Hello, I'm Gary Klinkhammer. I'm a professor at Oregon State University in the College of Earth, Ocean, and Atmospheric Sciences. Anyway, I should probably briefly explain the technology and then show you exactly what we got. This is the LiquID instrument, LiquID. So basically the concept is fairly simple. And all optical instruments have really two main components. They have a light source to create the light, and then a way to detect the light, so a detector system. And in between there, you have to contain the samples some way, so you usually have a flow cell. And so what we do here, we have a very intense flash lamp up here that flashes the light into the down to the flow cell here. Now the light gets from, and this is extremely important, the light gets from the lamp to the flow cell with a fiber optic. And so don't make the mistake to think that all optical machines are the same. They are not. This concept is totally different than the other optical machines out there. And the fact that we bring the light directly from the lamp into the water is extremely important and not done by other technologies. And so this gives us a lot of more energy into the sample, and putting a lot of energy in the sample is a really important part of what we do. You have to put a lot of energy in so you get a good result out. Also, of course, because it is an optical machine, we can make these measurements incredibly quickly. So we're measuring things 50 times a second here, so we can make a lot of measurements. In a place like a waste treatment plant, that's really important because the mixtures are very complex and you have to make a lot of measurements in order to be able to get a good answer. So we're bringing the light into the flow cell, we're taking that light and bringing up through another fiber optic into the detector system up on this side. So this is all what we call the dry box, and down here is where the sample comes in and into the flow cell. The measurement is made and then leaves the system and goes to waste. So this is a totally flow-through system. It's a very simple system, and that's important because in these really messy systems like we have in a lot of places for wastewater, we have to have something fairly simple so that sample can move through there without being obstructed and occluding everything. So we have a simple flow-through system. We have a very intense lamp system. We have a very, very good detector. And this is another very good distinction between what we do and what other people do. This system is a high-end detecting system. It's a photon detector. So it actually counts the photons. It's not an analog system. It's not even a digital kind of analog system. It's measuring actual photons and it pins on the detector and counts those, and you get a rate out of that. And that rate is very quantitative, and that allows us to give better answers. And so what do we have to talk about, since this is a really deep concept to kind of get your head around. It's really a different methodology that we're applying here. Now, methodology has a lot of aspects to it. For one thing, you have to apply methods and techniques, but you also have to have a unique technology, and you put that technology all together into an approach, and that approach is what we give, what would you call, the total package of all these components is what we call a methodology. And the methodology that we're applying to wastewater is unique. It has never been done before. So in a wastewater system, we want to measure something called biochemical oxygen demand, or related parameters related to that kind of concept. This is a concept that was invented back in the middle of the 19th century, so it's been around for a very long time. So people have developed various ways to get at this answer, but none of them have been very satisfactory. Using this technology, we can get a much deeper, more satisfying, and better answer for these problems than has ever been done before. How do we do that? Because we have a system that's broadly based, we can make different kinds of measurements using the system. So this measurement, in the most basic measurement made optically in the environmental science today, is light absorption. So you look at the light and you see how much of that light is absorbed by the sample, and then you get an answer from that. Okay, we can do absorption measurements very well, but our technology goes a lot further than that. We can also measure something called fluorescence. Fluorescence is the excitation, has to do with the excitation of the sample by an intense light beam and the measurement of the resultant energy that you get during the electron transfer process that occurs during that activity. So this fluorescence is an incredibly sensitive measurement tool, and it's a technique that's been applied to everything from studying DNA to looking at the smallest things that we can imagine. So the beauty of fluorescence is it's incredibly sensitive to chemical changes in the system. So our approach is fairly simple. We take these two techniques and we apply standard methodology to them to get a very solid answer using this incredibly good detection system we have over here. The other problem with the traditional, conventional way to do this is that usually it takes a long time. A conventional measurement of biochemical oxygen demand takes 5 days by convention. And so that really gives you kind of a looking through the backward mirror look at the chemistry of the water that you're interested in. You find out what the chemistry was 5 days ago, but 5 days ago the water has already left the plant. So you're kind of always working in the past. So this is why we have to come up with a better technique, and this is why we came up with this methodology. This methodology allows you to make the measurement continually, so you can look at the chemistry that's going on now. So you can adjust your process using this view of the chemistry and make your process better. That's the whole idea here. And we need better process, and we need a continuous view, and optical measurement is the only way you can really do that with current technology. We are looking at molecular bonds all the way from carbon bonds all the way through nitrogen bonding, and also other parameters that also are indicators of what's going on in the wastewater treatment process. Ammonia, total suspended solids, nitrate, other things that go into the microbial degradation process. So we get a good view of what the status is of the water, and then eventually is deemed good enough to discharge back in the environment. So it's important to be able to follow all these steps and then be able to monitor it and meet regulation before you discharge the water. So this is what our machine can do for you. Yeah, the idea of chemicals or other costs associated with a typical instrument are non-existent here. This is a totally optical machine. We don't use any reagents. We don't have any routine maintenance that's necessary on a daily basis. Like I said, the system maintains and calibrates itself. Combination of a new approach. We didn't reinvent anything here. We're using standard techniques. Fluorescence and absorption measurements have been around forever. There's nothing new about that. We're just making them very, very well. And then we got, standard ways of looking at these fluorescence and absorption signals in the wastewater. A lot of this work has been done and has been available in the science literature for a long time, but people never had the technology before to really be able to do it. We have the technology. This is a hybrid, hyperspectral machine, and that's never been applied to these problems before. So that's important to keep in mind as we close here, to understand that this is unique technology that's been designed for this kind of work from the ground up.